Okay, in this video we are going to talk about integrals and population density and finding total population. So let's see what we're dealing with. So the basic idea is going to be that you know some function for population density and it's going to be defined somehow. So you're going to be told that x, the variable, is the distance from like the left side of town or the right side of town or the bottom of town or something like that. You also have some description of the region where the density applies, and often there's a picture provided, which is really nice. And when I do these problems, I tend to think of Riemann sums all the time. So my advice would be that slicing up the picture can help you a lot. So let's take a look. We're going to do two that are, there's really no reason you to use calculus for, but we're going to use calculus anyway to kind of develop the idea. Then we'll do one that you definitely would need calculus for. So the first example we're going to look at is our population, which is rho, which when I draw rho, it looks exactly like a P. But rho of x is 200 people per square mile. So it actually doesn't change, so it's a constant, which means we should be able to do this geometrically. And in this case, x is the distance from the left edge of town, and let's take a look at what town is going to look like in part A. So here we just have a rectangle. So it's a 5 by 4 rectangle, so 5 along the x-axis, 4 along the y-axis. It's a rectangle, so you could actually just find the area of that. So the population is going to be, so the population here, it's just going to be 4 times 5 is 20 times, so that's 20 square miles times 200 people per square mile, gives us 4,000 people. So we don't really need calculus for this, but if we can do the calculus on this and get the answer, it might help us understand more challenging questions. So let's do that. So first thing that I'm going to do is I'm going to draw a rectangle. And so for this rectangle, I'm going to have a delta x. And then with delta x, I can now kind of find the area of that particular rectangle. So that I'm going to call that rectangle number 1. So that's my first rectangle. And it has an area of delta x times 4. And that's in square miles. So since delta x is made along an axis that's measured in miles, delta x by itself actually has units of miles, so that's miles times 4 miles, so miles squared. And then if I multiply that by my density function, which is in people per mile squared, the units on my final answer are going to be people. So this that I've written here will let me find the population in that little strip. Now what I'm going to do is just make more strips. So here's a second strip, so that'll give me a second rectangle. And for this rectangle, the number of people is going to be the area of the rectangle times the density within the rectangle. So it'll look like this. And then what I want to do is do that a lot. So I'm going to basically make kind of like n rectangles, all of which have delta x as their base. And in this case, they all have 4 as their height. So we end up down here at the nth rectangle. That's going to have an area of 4 times delta x. And then I'm going to multiply by the density within there, which is rho of x sub n. And so if I wanted to, I could, this is going to give me the exact value in this case, but not generally, but the total population should just be add all of those up. So I goes from 1 to n, it's going to be 4, the delta x, rho of x sub I. And then if you remember when you learned about Riemann sums, when you take the limit of these sorts of summations, they become definite integrals. So the actual total is the limit as n approaches infinity of that summation, which is going to be the integral. And then so delta x is along the axis that goes from 0 to 5. So my bounds are going to be 0 to 5. And then it's going to be just kind of converting everything. So the 4 remains the same. It's going to be rho of x, right? Because when you take the limit, the x sub i's just become x. So it's rho of x, but that's just 200 in this case. And then the delta x becomes dx. So we get this. If we evaluate this integral, however you want to do it, we actually just get 4,000 people, which is exactly what we were expecting. It's a lot of work to get something that we already knew the answer for. Let's do another one where, again, it's going to be a lot of work to get an answer we could get geometrically, but then we'll do one where you just need the calculus. So here, it's the same density function, so rho of x is 200 people per square mile. X is still the distance from the left edge of town. This time town is a triangular shape for some reason. So it's a 7 along the x-axis by 8 along the y-axis. So I could actually just calculate the population right now. It's going to be the area, which is 1/2 base times height, and then times the density, which is 200. This only works because it's a constant density, though. And also, I guess, because the bound is nice and linear, and I can find geometrically that area. So I'm expecting to get 5,600 people when I go through and do this. So I'm going to do the exact same thing. I'm going to create a rectangle, and the rectangle's base is going to be delta x. The height is more complicated in this case, so I need to actually kind of figure out this point, because the y value of that point is actually the height of this rectangle. So that point's going to be x, comma. So this is a line with a y-intercept of 8. You go down 8 over 7, so it's 8 minus 8/7 x. So that's going to be the height, 8 minus 8/7 x. So I can find the area of this rectangle is going to be just delta x times the height. So the height, I'm going to use x sub I here, so it's 8 minus 8 over 7 x sub I, or x1 I guess I should say, because it's the first rectangle, times the density, but the density is a constant, so I'm just going to plug in the 200 there. But in general, that's rho of x sub I. I would do this for a lot of rectangles. So create all these rectangles, find all of their areas, multiply by all the densities within them. So then I would just want to add it up. And you can see here I'm just getting an approximation because I'm missing out on all those little bits of area. So it's a sum from 1 to n of delta x and 8 minus 8/7 x sub I, and then 200, or I could have said rho of x sub I, but in this case it's constant, so it's just easier to write 200. So if I take the limit as n approaches infinity of this summation, it's going to give me the true population. And this is going to, so the limit of the summation becomes the integral. Delta x is along the x-axis, so my bounds come from the x-axis, so 0 to 7. The function for the bound, instead of x sub I, I'm just going to have x. Move the 200 to the front because it's just constant multiple, and delta x becomes dx. And then I just use a calculator, and I got 5,600 people. So it gave me the answer I was expecting, and that's good because this next one that we're going to do, there's really no way we could do it geometrically. So let's take a look. So rho of x is 3,000 over x squared plus 2 people per mile squared, and x is the distance from the left edge. And again, we have a triangular region, which is kind of nice. So this one, if you just kind of think about it, when x is 0, you get 3,000 over 2 people per mile squared. When x is, I don't know, like 4, you get 3,000 over 16 plus 2, so 3,000 over 18. So as you get further from the left edge, the people per square mile just decreases. So for whatever reason, people want to live along the left edge of this town. So let's see if we can do this. So it's going to be the exact same process. So first thing I'm going to do is draw this rectangle. Has a base of delta x. I need to figure out the height, so I need this point. So it's going to be x, comma, y-intercept of 9, down 9 over 6. So we can write 9 minus 3/2 x. We can then find the population within this one rectangle. So the population in this rectangle is going to be delta x times 9 minus 3 over 2 x sub I, or x1 really, but in general in a rectangle it would be x sub I, and then we need to multiply by the density within the rectangle, which is just going to be rho of x sub I. So we get that. So that's the population within any one rectangle. So we could have a bunch of rectangles, and then if we take the limit as n approaches infinity, that summation that we would write is going to become a definite integral. So it's the integral from, so delta x goes from 0 to 6, so the bounds will be 0 to 6. And then our function is 9 minus 3/2 x, and then we're going to multiply by rho of x, and then delta x becomes dx. Then we grab a calculator, and you come out with a approximate answer here of 18,945, and then the units on this are people. Okay, so that's 3 examples of how you can kind of solve these density type problems. I'm going to come back in another video and do radial density problems, which are a little bit different, but very much the same idea. I hope you found this helpful, and good luck.